Good morning or good afternoon, everyone. Thank you so much for making the time. We'll take another minute or two and then we'll get started. All right. Well, looks like we actually have a good number of people joined already, so I don't want to keep everybody waiting. So I'll slowly get started here as more people come in. So thank you so much for making time today. My name is Lucas. I'm the founder and CEO of pganalyze, and today we'll talk about proactive Postgres practices that help you prevent performance bottlenecks. And this is something that, basically comes from the experience that I've collected over the years, and that, many other people have also written about or shared in other forms. And I'm basically, kind of trying to summarize some of my own understandings of what I think are good Postgres practices for you to implement in your organization with your databases. This was partially inspired by a Postgres performance checklist we put together last year. This was basically a two-pager that we shared at some conferences that we got a lot of good feedback on. The idea behind the performance checklist was basically, if you're a database team and let's say you have 10 databases or 100 databases or 1,000 databases to manage, it does help to, have some consistency on the kinds of things that you look at on a weekly or monthly basis. And so with the performance checklist, we basically, put that together as a quick, here are the things you should be checking on a somewhat frequent basis or have a method of doing them, kind of in a predictable way. And today we'll talk about some of these things that are on this checklist. I want to go a little bit into more detail on, kind of specific practices on, how do you think about your database? What can you do to basically prevent particular pathological behaviors that happen on Postgres, for you to basically catch them ahead of time, so that they don't become a production outage, for example. Now, we'll talk about four things today. And these are, kind of, some of these are bigger chapters, some of these are small chapters. We'll run for about, I want to say 50 minutes, maybe a little bit shorter. And then also, if there are questions, I should point out that we have a Q&A section here in Zoom. So if you have questions, please use the Q&A feature in Zoom to ask a question. We'll come to questions at the end, unless there's something really, urgent, and I'll catch it. Then I might answer it as we're going through. But otherwise, please, queue them up and then we'll talk about them at the end. If for some reason we can't get to all the questions, we'll also send you an email with the remaining Q&A as well as the recording tomorrow at the same time. So if you have any colleagues of yours that are interested in this content and that weren't able to attend today, feel free to forward them the recording as well as the other resources we have. Also, I should point out, here with me today is Laura, who helps me organize these things. And Laura put together some resources already that you'll find through the Zoom resources feature. So if we mention some things, you'll see that in Zoom as well in that email that we share. So the four things we want to talk about today is, I first of all want to start by basically talking a little bit about Postgres and specifically Postgres IO. I find that when we think about, how do we make a healthy database, it's really important that we have a good sense for how the database actually functions, right? Like if we run a query, what's the actual, effect on the internal state of Postgres, or how does the internal state of Postgres relate to query performance, right? So this is not necessarily a preventative thing in itself, but it's more about how can we understand Postgres better so that then we can do the right preventative actions. In the second chapter, we'll talk a little bit about how we can tune Postgres internal bottlenecks. So this is, both monitoring them, finding them, detecting them, understanding them, right? Things like checkpointing or wall buffers that can lead to issues as your database grows bigger. And so we'll talk a little bit about what these are. We have focused on the IO side of things, I would say, as well as some other, internal caches. And then kind of how you can take action, like increase certain caches or maybe, change your workload in some cases. Now, on the third chapter, we'll talk about table and index maintenance. This is something that we've spoken about at pganalyze before. pganalyze does some of these things for you with features like index advisor. But today we'll talk more about specific, just general good Postgres practices. And it's important to say, with any of these things we'll talk about today, you do not need to use pganalyze. These are all things you can implement, just on a regular Postgres database directly. But pganalyze will make a lot of these things easier if you are a user of pganalyze. And then last, we'll talk about optimizing queries, a little bit about connections, connection pooling, and about wait events and when wait events matter. And a lot of that ties back to the earlier chapters. So it's really related to, If we don't do table maintenance, then that causes our queries to slow down, things like that. All right, let's jump into and talk a little about how we can think about, Postgres I/O and how that works, basically, right? So nothing magical here, right? But I basically want to remind you what happens when you write to a database, right? Is ultimately Postgres has to write that to disk. And when Postgres writes things to disk, it writes to both the data directory as well as the wall, like you write a headlog in Postgres. And you can influence how this process works. We'll talk more about that in a moment. But it's important to think about the fact that your client does an insert or an update statement. Postgres has a lot of logic around that and a lot of guarantees around making sure it's crash safe and whatnot. And so a lot of these things we think about in internal bottlenecks are really around write activity in Postgres. Now, let's break this out a little bit. If, in our function, in our application, we might have an activity like update this record. That might be one or more update statements. And then each of those might affect, one or more table pages and one or more index pages. It's important for us to think about not just about the logical aspect of this, but really the physical on disk aspect, right? So a lot of times when Postgres goes bad, basically, it goes bad because the on-disk state is in a bad shape. And so I think for us, it's really important to basically be aware of, how is Postgres doing, not just logically, but really physically on disk with the actual files that store our information. Now with reads, it's similar, right? Like a read happens from a data directory, also from, internal shared buffer state. And so, we can influence how read IO behaves. We can, improve the parallelism, for example. We can improve our indexes, improve our caching. So we do have control over that as well. But it's important to think about, that again, here, the physical state makes a difference, right? So how many index pages we have, how many data pages we have, like on the table, that really makes a difference. And for the ORM, it might be as simple as finding a record, but then really, that single row might have had a lot of effort to get the data, right? And so again, if I think of a healthy database is one that also is efficient, right? So basically that doesn't do a lot of unnecessary work to return one row. And assuming you have a good query plan, that is really mainly a function of bloat in your tables or your indexes. And I'll also say about I/O in general, the best I/O operation is the one that didn't happen because we avoided table bloat, or we, let's say we have an index, right? We didn't have to do the I/O. And so I think it's important to think about how can we basically reduce I/O to keep a Postgres database healthy. Now, the other thing I want to make sure you have a good picture of, because we'll talk more about that in a moment, is the internal caches in Postgres. So basically Postgres has two caches except for when you're on Aurora. And also if you are on probably Postgres 18, there might be a way to turn off things so it's just direct I/O, although not recommended in production. But basically we're moving towards a world where only one of the caches really will matter eventually. But in practice today, these two caches exist, which is Postgres's own buffer cache. That's what you control with the shared buffer setting. And then the OS page cache, which is your operating system, caching things internally. And so the visibility you have, in terms of statistics, is really better on the Postgres buffer cache than is in the OS page cache, because the page cache is just doing things behind the scenes for you, versus the buffer cache we can, query and monitor it. And so the things to think about there in the shared buffer cache is, and we'll come back to why this matters, but basically, each of these, let's say you have a default of 128 kilobytes of shared buffers. That's very small, but it's the default that Postgres ships with. And that, each of those has an 8 kilobyte page. Now, these 8 kilobyte pages might have, actually, that's not true. Postgres ships with megabytes. So I have 1,000 difference there. So Postgres ships with 128 megabytes of shared buffers. We are showing 128 kilobytes of shared buffers. Otherwise, that wouldn't fit in the screen. But the important distinction here is between basically different states of these internal pages, right? And the reason this matters is because you can get contention or, basically run out of space here if your workload grows. So for example, when Postgres, actively uses a buffer, actively uses one of these, table pages, it will pin this buffer and will be able to basically say, that's mine, right? I am actively using it. It will also sometimes write to a buffer, and that write will not yet be persisted to disk, and we'll get back to when that matters. But basically, dirty buffers are actually a very important metric to be aware of, and who writes out these dirty buffers to disk, because that's where you will find bottlenecks as you scale Postgres. Unpinned buffers, on the other hand, those are basically unused, but they may still contain some cache data, right? So this is a cache, but it also has other like kind of benefits. But on the caching side, really, a lot of the unpinned buffers are basically just keeping the data around so that you don't have to go to disk or the OS page cache. So yeah, we could talk more about details here. I'll not go into all the information here on the slide, but basically just be aware that these buffers change state, right? Like things move from unpinned to pinned when you're using them, and when at some point it's unused again, it goes to unpinned. But basically, you have to understand these core mechanisms to make changes, right? Or to understand where Postgres bottlenecks. Now, this is going to be, quite information dense chapter. But why do I want to talk about internal bottlenecks? I think a lot of the proactive work we can do is either going to be on a table or index side, or it's going to be around these internal bottlenecks that are basically, something in Postgres has to process your data, has to process your workload, kind of, your queries, and it's just overloading Postgres over time, right? And so when we think about preventative practices, in this chapter, we'll really talk more about these core functions in Postgres and which settings you can use to control them, also how you can monitor that. Because sometimes, a good practice is basically knowing about these behaviors ahead of time so that instead of, you hitting a bottleneck, that a workload, for example, requires a lot of, writes and requires a lot of synchronous commit. And so then you can kind of, tune wall buffers, for example, ahead of time, right? So things like that are important to know about. We'll start talking about checkpoints, and then we'll talk more about things like wall buffers in a moment. So when you think about Postgres, Postgres making changes, you have, kind of your wall, which basically that's, an immutable log where things get written to as you change them. And you have the data directory, which is basically files on disk that just get, the current state updated. Now, the hypothetical scenario that we need to think about is that things can crash, right? That's a lot of the job a database does for us is it gives us crash safety so that if things go bad, we are still in a good state in terms of our data isn't lost. And crashes are rare, but they do happen, and you kind of need to really plan for the 1% use cases here. The other thing here is to think about is what is the current state of the data directory, right? Because what might happen is that the data directory isn't actually fully synchronized up to the changes that were made in the wall. And so there's basically certain guarantees we will have about what the actual state is and what the consistent state is. So Postgres has these checkpoints, which we'll talk about in a moment, but basically think of a checkpoint as a known defined safe state. Now, let's say in this moment we crash, right? Like something happened. Now, in the moment of a crash, we basically know that the data directory was in a certain state as of the last checkpoint, and we know all the wall records after that checkpoint, right? So we can basically say we know the data directory was, written to disk at the checkpoint time, and then all the changes that were made in the wall records afterwards let us recover, right? And so we can basically go back to that moment in the middle here, like that kind of thicker that kind of line in the middle that lets us basically recover to the safe state. Now, one of the things to think about of these checkpoints, right, these safe moments, is that there is a choice here. And this actually is something you need to think about as you grow your database and as you kind of, think about, is my database in a good state? So the ideal checkpoint is a timed checkpoint. Time checkpoints in Postgres happen by default every 5 minutes. This is something you can tune with the checkpoint timeout setting. Think of this as basically a cron timer of sorts, right? It just runs and it says, now it's time for another checkpoint. And the benefit of time checkpoints is that they smooth out the I/O over time. So the difference here is think about, the alternative, which is called a wall-based checkpoint. A wall-based checkpoint has to basically force I/O to happen quickly, versus a time checkpoint basically knows it's going to run for 5 minutes, right? Like the next moment, the next point in time where it needs to be in a defined good state is in 5 minutes. And so it can smooth out the I/O it needs to do to flush, information to disk. It can smooth that out over a 5-minute time frame. And so you'll see if you get a lot of time checkpoints, your workload will be more predictable, versus if you have a lot of what we're called wall-based checkpoints, you'll basically get a lot of I/O spikes when these wall-based checkpoints happen. The reason it's called wall-based is because these happen because you have too much write activity, right? So this is one of the things that I think is very common for people to tune. But if you don't notice, right, like be aware that if you have a write-heavy workload, you'll likely have to increase your max wall size because the max wall size basically controls how much wall can be accumulated, right? How many changes can be accumulated within a given time-based checkpoint. And if that is exceeded, then it basically forces a wall-based checkpoint, which causes an I/O spike. This is something you can tune, right? Like for example, here is one of our own databases. We have a max wall size of 50 gigabytes. That's something we intentionally change to basically optimize the checkpoints. Now, here's one of the ways you can analyze this information is you look at your logs. So this is a screenshot of pganalyze, but you can look at this in basically any logging tool. You use the log checkpoint setting in Postgres. That's turned on by default nowadays. If in older releases, you might have to do log checkpoints on. And what it does is basically says every time a checkpoint starts, it will emit whether the checkpoint that is currently starting is a time-based checkpoint or an Xlog or wall-based checkpoint. And then what you want is that the screen looks like it does here, which is you basically have mostly mostly time-based checkpoints with maybe the exceptional wall-based checkpoint. Whereas if you had a lot of wall-based checkpoints, that basically means your workload is spiking, right? And you don't get that smooth I/O behavior that you want. And so this is, for example, something I would look at, maybe on a monthly basis on very busy, important databases, is getting a sense for how your checkpoints are behaving. Now, a related concept when you think about checkpoints is what we call full page writes or full page images. So full page images are basically copies of the original table pages written into the wall. And the reason they exist is because of something called torn pages. So what can happen is that you basically have the data directory not in a perfectly consistent state, meaning something, when it crashes, you have basically half a file. And the problem is, in that situation, if you try to apply the wall, you basically get an inconsistent situation. And so what a full page image does is basically can copy those full page images from the wall into your data directory to fix those torn pages. This is a very important safety feature. Now, it is very dependent on whether your storage actually has this problem. And so sometimes you can turn this off if you know your storage really well. So this is a setting you could technically turn off. But most of the time, I wouldn't recommend this. The thing to understand is that as you have checkpoints, the longer there's a distance between checkpoints, the full page images decrease over time. And that's because you need basically the first time when a checkpoint happens, like the first time a write happens to a page after a checkpoint, it has to be a full page write because you basically need the wall to have a kind of a known good state of each page being modified. And so if you keep changing the same page, within that same checkpoint timeframe, basically, it's not going to change again. But knowing about these, full page images and how many of them you're producing is really important because it does influence how much wall you're generating, right? Like this is one of the bigger parts of your wall stream, basically. The other thing to know is that there are compression settings you can use here. So for example, starting with Postgres 15, you can use wall compression LZ4. That's something that, will basically do a little bit of CPU overhead, but not a lot. Like previously, there was the pglc format, which was really inefficient, but LZ4 is relatively efficient. And so that helps you basically, keep the wall stream smaller by compressing these full page images. Now, it's also important to think about, so that's on a checkpoint thing, but let's think about again what happens when we write out data. So shared buffers, right? Like they're, as I mentioned earlier, they're not just a cache; they're really essential for Postgres writing information, right? So when we make a change, we remember that change in shared buffers. We also, remember the change in wall buffers, and wall buffers are basically where that changes ultimately get written to the wall, and then things get persisted to the data directory. Data directory persistence, that's the checkpointing. The wall persistence, that's basically dependent on a couple of settings you have. So maybe first, important to mention here is what's this core mechanism, right? Like how the writes actually happen in shared buffers. So we talked about earlier, we have a pinned buffer. That's one that's currently being used. A dirty buffer is basically after the pin is released, right? Like, and now it's ready to be written to disk. And so something can write it to disk now. The reason that Postgres doesn't do these writes immediately is because it's way more expensive to do them, individually than to do them all together and then flush them, right? Which is, for example, what the checkpointer can do. This writing the data from the memory to the OS page cache or the flushing the OS page cache to disk, that's something that either the checkpointer can do, the background writer, which is a dedicated job that does this, or individual backends. Now, here's the thing to watch out for again. This is important preventative practice again, is you do not want that third case to happen. Like you do not want individual backends writing. And so if you see performance regressions, sometimes like individual queries suddenly being really slow, like a simple select statement behaves odd. It can happen that's because of the backend basically needing to write out data. So background writer, that's cleaning up our table. But then really, the thing to know, to look for is individual backends doing that. Now, starting in Postgres 16, we have pgstat.io. pgstat.io is really an amazing, tool that we have at our disposal now to look at by basically where the writes happened in Postgres. And it can help us answer many different questions, but one of the things it can answer is which part of Postgres wrote something to disk, right? So this process of going from a dirty buffer to having written it to disk, that's what pgstat.io can help us answer. And so we see here is we see basically the backend type that caused the IO to happen. The object, like this might be, a temporary table, for example, or just a regular relation. And the context. Context is what's interesting here for us is normal, but there's like bulk write or bulk read facilities in Postgres as well. Now, with this particular query, what I'm looking at in pg.io is for these writes, right? Like for these, that effort basically that happens, where does it happen? Like who writes out their dirty buffers to disk? And so this write on the screen is a good state. This is either the background writer doing a writes or the checkpointer, both of which, like the checkpointer, will smooth them out nicely. The background writer just does them, over time. Like both of them basically are the good kinds of writes. The bad kind of write is when a client backend does a write, as you see here in the top. Now this is, over a longer time frame, but basically, the relation here clearly shows that, not many client backends are doing writes. On the other side, if this is from a presentation that Melody Plagueman did 2 years ago, where she talked about the I/O observability of pgstat.io. Great presentation. I would recommend looking at those slides. But basically, in that presentation, she shared a pathological case, which is, as you can see here, the client backend basically doing as many writes as the background writer, and then a checkpointer doing very little writes. Right? And what that means is that what is supposed to be a background activity shifted into kind of the actual front end, basically like the client backend's doing the work, like the actual, you're running a query, and it's slowing things down. And so you can monitor this with pg.io, and you can, this will oftentimes get worse over time, right? Like as you're basically increasing your workload, so that, the client backends have to do this work, because it doesn't happen on schedule. Now, there are certain things you can do. So, for example, you can tune, apart from checkpoint tuning, as mentioned earlier, you can also tune the background writer specifically. So you can have the background writer write things more often. So it's worth considering basically, tweaking this if you see a lot of writes done by individual client backends. But be aware, you don't want to tune it to run all the time, because one of the benefits of, not flushing things to disk yet is that if something is dirty and it gets changed again, you don't actually incur extra I/O, right? So you're basically saving an I/O if it's not written out to disk yet. And so this is the reason why you don't want to do this all the time. Like you basically want to do this enough that you don't have the clients, the backends writing out, but not too much that you're basically causing all the extra I/O. And let's talk about wall buffers. So wall buffers is another setting you control, and you have to tweak on some databases over time. So wall buffers basically are a staging area of sorts until data gets written to a wall file. Now, in the regular operations, it would happen on a commit, right? So you have your insert statements, and then assuming you don't write more than, for example, 60 megabytes, if your wall buffer is 60 megabytes, just keep staging data in the wall buffers in the memory, and it writes it to the wall file. Now, wall buffers is automatically sized based on a default setting, like -1 means it just picks its size based on a shared buffer setting. it can make sense to tweak the wall buffers to basically increase the amount of things you keep in memory. Really, this is if you have big transactions, right? So if you have a lot of data being written as part of one transaction, or if you're using synchronous commit. And in those cases, if you're turning off synchronous commit. In those cases, what makes sense is basically to increase wall buffers to a multiple of wall segment size, right? So here on this picture, wall buffers is smaller than the wall segment, the wall file. Like here, it's 1/4 basically. But it might make sense to make the wall buffers multiples of a wall file in some workloads. Now, one of the key settings you can do, and this is, I consider this, a preventative practice because it really strongly influences how Postgres does I/O and writes to the wall, but it is a choice that you have to make in your workload. So synchronous commit, basically the trade-off we have to do here is a crash safety trade-off. So if you have really critical data where you cannot lose a single transaction, then you should not be using synchronous commit off. But sometimes it's okay to use this because sometimes, in the case of a crash, you're okay with losing the most recent write because you have some other mechanism of repeating it, and you basically, want to only guarantee certain transactions. So in the situation where you have synchronous commit on, what happens is what we showed earlier, right? So like insert statements are happening, and at the commit time, we have to basically flush that out to the wall. If synchronous commit is off, what we can do is we can actually keep wall buffers around, and we can only write at the time that either the wall buffers are full or based on the wall writer activity, basically. And so the big improvement here is that we reduce the amount of I/O that has to happen at one time with individual transactions. It also means that the client doesn't have to wait, right? Because this can happen in the backend, right? Like Postgres can do this activity whilst the client already got the insert returned, basically. And so really what happens is that you're basically losing the data, like the most recent transactions. There's no risk of actual corruption. It's just you're missing that data, right? So again, it really depends on the kind of data you're working with and how much you would be impacted by a crash. Now, the most important thing to know, and this is a lot of people don't know this, is that you can change synchronous commit for each transaction. So you can have one transaction be synchronously committing and others asynchronously committing, which means that if you have, I'll give you an example, right? Like pganalyze itself, for example, has time series data. Our time series data, it's important, but if, a single data point was lost, it's not, terrible in a crash situation. Versus, let's say, our users or company data, like billing information, we want to make sure that that's perfectly, synchronized, right? And so we could say that, for anything that's the time series data, let's turn synchronous commit off. For anything that's, critical metadata, we don't turn it off, right? And so that's something you can basically affect on an individual transaction basis. Also, worth thinking about is you have some control over that wall writer. So the wall writer has a delay setting. You can also, as mentioned earlier, you should probably increase the wall buffers so that you really get benefit of that, bunching data together. It's worth noting, just in terms of observability on these settings, that there's some observability into, kind of how much wall do individual statements write. But wall buffers directly, to my knowledge, you don't really have that great visibility. There is pgstat_wall in newer releases, which may give you some, introspection there. But yeah, basically, a lot of this will come down to what trade-off are you okay with making, right? So it's more of a talking to your application team and saying, are we okay to turn this off? Because you can basically get a lot more out of your database if you do. It's also worth noting on the wall segment size, that's basically the size of the wall files. This default 60 megabyte is probably too small. It makes sense to increase that to 64. If you go for much larger files, it makes sense to also increase the min wall size, which basically avoids Postgres removing old files. Like basically, let's suppose you have a 64 megabyte sized file. Just creating that on disk is expensive versus what Postgres can do is it can recycle them, so it can reuse the old files. And so it makes sense to also tune that wall size setting. And I want to conclude, talking about checkpoints and wall here by mentioning that Aurora is different, right? So if I'm sure many of you here are using Amazon Aurora, and Amazon Aurora has its own intricacies of how it functions. Some of these things are relevant, some of them are not. So Aurora generally, will remember change pages also in shared buffers. It will write out changes to the wall. The wall still exists, but the wall is then treated very differently with, basically a log write implementation. And that's also what's used to basically update replicas and kind of their shared buffers. That log writer is also the one that, does these famous 6 copies and whatnot of things. So basically, all that mechanism under the hood works differently. Now, one of the things that Aurora, for example, has done, and this is, sometimes you'll hear AWS claiming, 4 times improvement or whatnot on Aurora. Some of these things are basically just caused by not doing full page writes, for example, right? So like because they control the storage subsystem, they can turn off that setting reliably, and because they replaced a good amount of that. They also don't really have checkpoints in the same mechanism just because they basically modified that heavily. So some of these things that we mentioned don't really apply in the same way, right? It's worth checking Aurora specific documentation on some of these things. But suffice to say that, you still have to think about, IO happening and, kind of like all the things we talked about in terms of reducing IO do apply. It's also worth noting that Aurora isn't always better because unless you use the IO optimized version of the instances, you do actually pay for read and write IOs. Read IOs are always charged at the disk pages. They will be slower a little bit on Aurora than a regular Postgres because there's more work being done. And write IOs are also charged per log record basically. And if you use synchronous commit, that will be slower. Synchronous commit off does work on Aurora and does make sense on Aurora if that trade-off is good for you. All right, let's talk a little bit about something very different, which is still internal, and then we'll move on to table and index maintenance in a moment. So SLU caches. SLU is a term for simple least recently used. Now, SLU caches are basically, and I took this definition from a presentation that Thomas Munro did a while ago, they provide storage management and buffered access for 7 kinds of critical transaction-related data. 7 is not a magic number, it's just the number of SLU caches that exist today. There could certainly be an 8th or a 9th. And they basically got added over a couple of Postgres releases. They basically serve very specific purposes, and they're all kind of transaction related. So maybe an easy one to explain is the commit timestamp SLU. That's basically if you enable the commit timestamp feature, this is what would actually save the timestamps for each commit. Multi-exects, for example, are stored in SLUs. Those are basically implement row level for share locks, like using foreign keys and whatnot. The notify queue, list notify queue, is also implemented as an SLU, as is the information that's kept for serializable, as is some information about transaction commit abort, as well as sub-transactions. Now, this might seem like an odd mix of things, right? Like list notify is very different than, I don't know, multi-exects, for example. But really what all these share together is that there's basically an in-memory cache of stored, an SLU cache, which has a specific size. And then there's an on-disk relation to this as well. So I just looked at this as a local data directory here that I had. And you can see, for example, pgnotify is the directory that keeps the on-disk data for list notify, pgcommitts for commit timestamps and such, right? And so basically these internal data structures in Postgres, they're responsible for, making sure you don't go to disk all the time for accessing things like a commit timestamp. Now, this is something we can track. The reason I think this is important to talk about is because it's the kind of thing that will surprise you because you don't think about it. Like it's the unexpected thing. So, for example, here, and this is one of our own systems, I just looked at pgstat SLRU, and I said which of the SLRU caches are basically where we have cache hits, meaning it goes to the in-memory version of the SLRU cache, versus where does it have to go to disk. Now, it's expected, for example, for a transaction status like the second to last one, exact, that it does a bunch of work there, right? Like this workload is basically it's a regular OLTP workload with bunch of time series data. For example, one thing that I know about, but maybe would be surprised if it was a lot more, was that notify also, there with a little bit of usage of the notify kind of activity in Postgres. We don't use sub-transaction, we don't use multi-exects. This is the good happy state basically. Now, there can be really unhappy states. So I picked two examples that I have looked at in the past, which is one is by GitLab, the other one is by Nelson Elhaj, where he worked with a client, I think. In the GitLab case, GitLab basically experienced the databases on GitLab.com would mysteriously stall for minutes, which would lead to users seeing 500 errors during this time. The reason that the database stalled was because these SLU caches basically bottlenecked in certain ways. In the GitLab case, it was sub-transactions, where basically this is why their blog post there is titled "Why They Spent the Last Month Eliminating Sub-Transactions," because basically what they were seeing is that they were hitting these internal bottlenecks and they didn't know what to do about it, right? Did a lot of investigative work, figured out, that it was those SLU caches, but they didn't want to patch Postgres at the time to increase the cache sizes, like on the in-memory cache, and so they ended up basically doing the application side work to remove that. Now, another case was Nelson Elhaj, where he basically talked about query latency spiking and the throughput plummeting virtually to zero. Sounds very similar to GitHub, and the database would completely lock up. In Nelson's case, it was multi-exec, but again, it was SLU related, right? So it's important to know about like basically what we're trying to do is we're trying to look at this data, like the SLU data, so that we know how our workload behaves, so that we do not end up like GitLab, for example. Now, Postgres 17 does actually make significant improvements that are worth knowing about. So you can increase the in-memory cache sizes. So you can say, I have lots of multi-execs. Let me keep more of that information in memory before it goes to disk. Also, the locks that are used for accessing those in-memory caches are now partitioned, meaning it's if your workload previously bottlenecked on these internal locks, now that's much less an issue. So what I would recommend doing in the context of SLUs is understand where you're using these SLUs and which type of SLU for a given workload. So you can either modify your workload, or if that's not an option, then certainly consider upgrading to 17 if you can, because that lets you tune some of these internal settings better. Now, last internal, and then I want to switch to table index maintenance, is I want to briefly talk about replication. So replication lag is ultimately a function of WAL, right? Because both a physical and logical replication, what you're doing is you're taking the WAL stream of changes in Postgres, and you're replicating that to secondary, to replica. And so less WAL writes means less replica lag, right? It's like if you reduce the amount of WAL you're writing, that directly correlates with less replication lag problems. If you reduce the number of full-page images you're writing, if they're active, that will also cause less replica lag because the WAL is less busy, basically. The main thing I want to talk about with application lag is the choice, like besides the WAL activity, the choice you can make, and again, this is something to think about proactively so you don't get surprised by it, is the setting of hot standby feedback. So hot standby feedback will imply, does the replica talk to the primary so the primary keeps certain information around? And so if you turn hot standby feedback on, which makes a lot of sense most of the time, what you will see is that the replication lag will be less. Also, you'll basically see queries not being canceled as much on a replica. But the downside is it can actually have effect on the primary. For example, it can block vacuum activities, right? So it's worth thinking about not doing this if you want to not impact your primary at all. If you turn hot standby feedback off, it will increase replication lag but avoid the impact. One of the best practices that I've seen implemented here is if you use like data warehousing type use cases and you make a replica for it, definitely do that as a separate replica from any like OLTP real-time workload, and then consider for the data warehousing workload to turn off hot standby feedback to basically avoid that bloating issue on the primary, and then increase the max standby delay so that you don't get cancellations, right? So you're basically intentionally taking on replication delay to not impact the primary. But that's the main thing I would say about replica lag today, outside of optimizing for less WAL. All right, I'll keep going here in the interest of time, but let's switch gears. So we talked a lot about settings. We talked a lot about internal state of Postgres. That's something that I want you to have a good understanding of, but I do think that sometimes maybe we can only do so much, right? Now, the parts where we have a lot more control over is tables and indexes. So I'll do a quick version of what is bloat and how we can detect it. I'll go relatively quickly here, but this is part of this content comes from a webinar we did previously in auto vacuum. So if you are interested in the long version of this, we can search for auto vacuum webinar on our website. But basically, if you think about what is bloat in Postgres, so think about, this is our table, roughly 100 kilobytes of data. Each green dot is 32 bytes, and each kind of, rectangle around it is 8 kilobytes, or one page, or one buffer, and share buffer terminology. Now, let's say we create a new table. We insert the first record. You see the little blue dots on the left there. They're basically, the space we're using after we did a simple insert. Now, let's suppose we insert a very large value, right? Then obviously we take more space in that table, right? Now, let's say we keep doing that, right? 48 more times. So we have 50 tuples in this table. Now this, basically takes all of that single page we have here. Now, one of the metrics you can look at is what is the density of my table, right? Like how many tuples or row versions do I have compared to, how many are on each page? So right now, that's, 50, right? Meaning we can fit 50 tuples on each page. Now, suppose I insert a little bit more data, Postgres has to allocate more space. Suddenly our density decreases, right? Like we have less information average per page because we just opened a new one. Now, bloat happens in this situation. So now we're deleting something, right? We basically go ahead and we delete everything that was there except for the very last thing we added. And now we have one live row and 50 dead rows, right? Now our tuple to page density is basically extremely low. Like we have less than a row of data per page. Now, the really critical question to ask yourself in terms of table maintenance is, did we get a vacuum that happened in time, right? Because suppose you're in that state where you deleted all that data, it's marked as a dead row, but then if that didn't get vacuumed in time, what will happen is we'll keep growing the table, right, to basically make space for more data. And so this space basically is where like let's suppose we have that vacuum happening, right? Now the space is reusable, but the table is still large, right? Like Postgres won't remove that page that doesn't have any data anymore. And so this is really what bloat is. Bloat is that empty space in a table that doesn't necessarily need to be there, right? Like if you basically put it together again, like if you took the table apart, took all the data out and made a new table, it would look very different. So just one example that we've ran into in the past is we had bad update behavior, bloated the table quite significantly, and so we actually ended up with just having. We had a table that was 500 gigabytes in size, but only 1.7% of the table was data. So clearly, not a good situation. And this can just happen, right? It's like these are the kinds of things that will happen behind the scenes because of your workload, because of auto vacuum in Postgres. So really, I like to think of bloat as basically less than optimal page density. Now, how can we detect that? So there are these bloat estimation queries. So the reason they're good is because they're fast. You can always run them without any impact. And the idea behind these estimation queries is simple. You're basically saying, what do we think the number of tuples is in the table, like number of rows? How wide is each of these rows? And various other things. And then basically we try to calculate the optimal size of the table if everything was perfect, right? And how does our current size compare to that? In pganalyze, we can actually graph this over time. So if you look at the graph at the bottom where it shows estimated table bloat, that's something we make available for every single table that pganalyze tracks. And we basically make this estimation all the time. It's really cheap to do. And we basically just say, what's the current, estimated data size and what's the current estimated bloat? You'll see that this fluctuates, right? So you'll see this is the red area chart at the bottom. It doesn't actually stay steady. It actually changes, showing you how, imprecise this estimation can be, right? So like this is not a precise number. Like the truth is probably somewhere in the middle. But it does show us that there is probably a chunk of this data, right now it estimates 60 gigabytes, that is not really necessary. And so what we can do is we can start with these fast estimates, but then we can use pgstattuple to verify it. Pgstattuple basically, lets you calculate the actual number of free kind of pages in the table. And then also if you use these bloat estimation queries, maybe run analyze before so you get more accurate data, various other cases to think about. But really this is something that, I would recommend having some mechanism to track bloat over time and flag things that have lots of bloat because you will have these inefficiencies in your database. Now, fixing table bloat, you might be familiar, but if you use vacuum on a bloated table, it will not fix the bloat. That's maybe the first important thing to know, because vacuum generally does not move things around in a table. Like it won't move a row from page A to page B or page one to page two. It just, can clean up things so that they're usable again. And so what you have to do is you either have to use vacuum full, which you should not use vacuum full because that's not made for people who run production databases. It's made for, people in a lab. But really, what you need to use is pgrepack or pgsqueeze. If you have pgsqueeze available, that's the more modern one of the two. So I would recommend pgsqueeze. But pgrepack also works with some caveats that you maybe should read about. But on AWS, we have repack available. So on AWS, for example, you can create the extension, install the repack client-side utility, and then you run that on a specific table, and that basically lets you clean things up. And so this is actual data point from our own database is where you can see we went from that 500 gigabytes of data to or 500 gigabytes of table size to I want to say less than 10 gigabytes, something like that. So, significant improvement just by, repacking it. And again, this was because vacuum wasn't working as expected. Talking about vacuum for a moment. So preventing new table bloat. It's worth thinking about auto vacuum schedules. Again, we have a longer presentation on auto vacuum, so I won't give you the full spiel today. But I do want to briefly mention this particular aspect. So tables get auto vacuums for two reasons mainly, either because they reach a certain dead row threshold or insert row threshold, or because of transaction wraparound prevention. So in this graph here, what we can see is basically the red line that indicates when an auto vacuum will start. And so Postgres, is predictable in that sense. So if that line isn't hit, then, like something else must have started, like a, transaction wraparound. But basically, this is, very deterministic behavior. So here, for example, this threshold is calculated based on a live tuple. So we have 120 million live tuples, live rows. And with the default setting of a scale factor of 10%, that means if we have, 11 million plus 50 tuples, then an auto vacuum kicks off. It's worth noting that Postgres 18 will introduce a new setting here that basically lets you control the maximum. This is in every current release of Postgres. This is basically the biggest issue of this, is that this number can get very large, meaning you will have lots of dead rows to accumulate, which can be an issue on large tables where there's lots of active rows, basically. And so Postgres 18 will have a way to tweak that. But basically, what happens in all current releases is that these thresholds, basically when that's hit, that's when an auto vacuum kicks off. There's also alternate reasons to kick off based on a transaction ID. Basically, what you should know is that you can tune this on a per table basis. And you might find yourself tuning this on a per table basis if you know that a table does not behave well about this, right? So you want to basically run vacuum more often to reduce the bloat from happening. So most common case is you have a large table, a small active portion of the table, right? So like lots of records, but only very few are being updated, for example. Then the scale factor setting is basically not good. And so what I like to do there is turn off scale factor 0, set the threshold to a fixed number. This is close to what the Postgres 18 setting actually introduces with a maximum there. But basically it says, threshold, if there's 10,000, tuples that are being dead, then we should vacuum. We also detect this in pganalyze. So it's worth pointing out if you use pganalyze vacuum advisor, vacuum advisor will look for these patterns and when they produce bloat, and it will give you these scale factor and threshold tuning recommendations. Let's briefly talk about index bloat. So index bloat is ultimately a bad index structure, lots of unnecessary index pages. Here's an example of a bad index structure. This is our own database a couple of years ago, actually, where we had a bad index and it was producing a lot of write IO. And you can see how, in the start of the day, when this was partitions, right? So in the start of the day, everything's fine and it keeps getting worse over time. And so this was, surprisingly enough, a single table causing this. And it was a single table causing this with random UUIDs. Random UUIDs are really, really bad because they're bad for the internal B tree structure. Like if you have a B tree and you have a random number, basically it will, cause the B tree to do lots of splits, basically, and lots of kind of unpredictable changes to the B tree. In this case, we at the time we ended up using ULIDs. Nowadays, there's UID v7. UID v7 is what I would recommend once you're on Postgres 18, which is the next release of Postgres. Or if on the client side, you can generate something like this. What a UID v7 or ULID is basically a timestamp prefixed UID. And so timestamp prefixes make it much, much better, to the extent that you'll see here, on the right side, this was basically where we tweaked this and we ended up, stopped using random UIDs. We changed it to time-based UID. Then, the right arrow was just flat, right, like on the right side. So the reason I pointed out is because this is because the internal structure of the index, right? Like the internal structure was just so bad that we kept recreating it, right? So to a certain extent, because this was a daily partition, it was actually less problematic, I would say, than it could be. But what's also worth thinking about is if you have a table that's not partitioned, right? So you keep writing to it, and you have, for example, a random UID or other kinds of activities to cause the index state to go bad, reindex concurrently on a schedule can be a good idea. So kind of getting a sense for, like bad indexes that keep being bad and then doing a reindex and it really makes it better. It might make sense to just do a cron job once a month and just do this at off hours because that will kind of keep the indexes optimal. In the context of indexes, I also want to talk about unused indexes quickly. So unused indexes are basically just adding write effort, right? And as we grow our systems, we have more and more unused indexes, which, they have no point, right? Like they're not even forcing any unique constraints. You're just writing to the database and updating indexes, but you're never reading them. And so pganalyze can detect that for you in the index advisor. One of the key things we do here is the last use column. So the challenge basically is that in Postgres, up until the last Postgres release, you couldn't know when an index was last used by timestamp. You basically had to do some like measuring things over time. Now pganalyze can do this for all major releases of Postgres. Postgres 17 can also do this built in. So Postgres 17 added a last index scan timestamp column. This makes it really easy now. If you look at pgstat user indexes, you can basically write a query that just looks for all the indexes that were scanned more than 35 days ago last time, and then that lets you basically drop these indexes if they are not a unique index, if they don't not needed by a replica, things like that. So great improvement in Postgres 17. Other things to consider in terms of indexes, and in terms of time, we don't have time to go into all of these, but generally vacuuming more often, or to tables is more table related. Vacuuming more often can reduce I/O spikes, right? So like vacuum might seem like the thing that Postgres does that you don't like, but really it's worse if you do it less often, basically. Hot updates, which we didn't have much time to talk about today, basically influence like the efficiency of updates in Postgres. And so just think about like research that if you have time. And when somebody adds a lot of indexes, tell them about hot updates. And then last, if you use gin indexes, watch out for the pending list in gin. We have a blog post about this. We have a blog post about this that we published a couple of years ago. But basically, gin indexes, the way that they write to the index is very particular. And so if you have an update-heavy workload with a gin index, then that can be pretty bad, basically, and behave unpredictably when that pending list exceeds its kind of configured size. All right. I realize I said 50 minutes. Probably looks like we will use most of the full hour. I'll make sure to use a few more minutes at the end for Q&A. But let me talk about optimizing queries, connections, and wait events for a moment. So what we talked about so far, all of it has to do with the internal Postgres database state, right? Like either the internal structs or kind of the table index kind of state and how we can influence it. Now, maybe a really quick reminder on how can you track query performance, because oftentimes these kinds of things do show up on the query performance side, right? Like really a bloated table will slow down queries. A bottlenecked SLRU will show up in a slow query. So one of the key tools we have in Postgres is pgstat statements. Research that offline if you want to take a look at how exactly it works. But basically, the gist is it tracks aggregated statistics on finished queries over time. That finished queries is an important thing to know. Stat activity shows you the currently running queries and current locking issues also. So if you want to know what's happening right now in a particular moment, stat activity is better than stat statements because stat statements only shows you finished activity. The Postgres logs can help you track timed out queries or canceled queries. It's worth noting that a finished query in stat statements does not include a timed out or canceled query. So canceled queries can be kind of hidden and can be a hidden workload in your system. So it's good to know if you're doing a lot of cancellations, you will need to look at the logs to really see, where the workload is coming from. And in auto explain, again, I won't have time to talk about this today, but if you want to talk about query plan outliers and identifying bad query plans, that's really where auto explain comes in. And so whatever you do, I think you should have some mechanism to track most of these, right? Like pganalyze will do all of this for you, but if you don't have pganalyze, I would recommend finding a way to at least track stat statements and stat activity over time. But really, if you want to have a complete picture, you really need the logs and auto explain as well. However, I do want to talk about two things. I want to talk about connection pooling for a moment. So connection pooling, happens because Postgres connections are expensive, and because they're processes, not threads. Still true today, right? Like was true 10 years ago, still true today. There has been a lot of work to reduce the overhead on the individual processes in Postgres, and there is an active effort towards multi-threading, which made some progress in Postgres 18, but won't be there. To be clear, Postgres 18 will not be multi-threaded, probably not even 19. I think this is more like Postgres 20 type conversation. So probably 2 years from now at the earliest. But there is a concerted effort upstream to say, how can we make multi-threading happen because it has efficiencies, because it lets you share memory more effectively, right? But today we don't have that. So today in Postgres, we have connections, and that's something we need to know about. Now, if you have less than 1,000 idle connections, I would say, don't worry too much about this, right? Like basically, if you're in the honeymoon phase of your database or your database is just small, don't think about it too much. But beyond that, really, it is important to think about connection pooling, think about something like pgbouncer or pgcat to really have, a mechanism to scale connections beyond that, 1,000 or a couple of thousand connections limit. So quick TLDR on how I would use a connection pooler effectively is on the left side, we have our application servers. In the middle, we have the connection pooler. On the right side, we have Postgres. Very important, do not consider your application server's own connection pool to be a pooler, right? So let's take Ruby on Rails for a moment. Ruby on Rails likes to have its own internal connection pool. That is technically a pool of connections. However, it does not have the intended benefit, which is it's mainly meant for reducing latency on the application, but it doesn't improve our reuse of connections. Really what we're looking for is that, kind of 10 to something ratio here. So like here it's 10 to 3, right? Like there's 10 connections to the pooler, but only 3 connections to Postgres. And so you're saving a lot of memory on the Postgres side with, that kind of ratio. Also important to note is put your network on the left side of your pooler in this diagram. So basically, if you think about should my connection pooler live next to my application or should my connection pooler live next to my Postgres, it will behave a lot better if you put it next to Postgres in my experience. And then, what the pooler does for you, right, is like it reuses connections, it reassigns which connection on the pooler side gets to Postgres. Now, the case to think about in terms of, thinking ahead when there might be problems is this bottleneck that can happen. So suppose there's 3 connections, right? And there's one more connection coming in. That connection has to wait until, another one is free. So this is one of the things to think about with connection poolers is this waiting in the pooler for something to be free is both a good thing and a bad thing. It means your queries might be slow because the pooler is making it slow, right? So do monitor your pooler, that's what I would say. But then also it can help you reduce the peak resource consumption in Postgres, right? Because you can basically force concurrency. And this is one of the really nice features of a connection pooler like pgbouncer, is that you can say, I at most want to have 10 active connections in Postgres, and I want things to wait if there's more than that, which there's no core Postgres mechanism to do that. Last but not least, I have 2 minutes left here on the regular scheduled time. Wait events. So wait events are basically something that, informs all of what we talked about. So wait events are like something you can track over time with pgstat activity. They tell you where your bottlenecks is for currently running queries. So here, for example, I took a snapshot. There was a particular wait event on IPC buffer IO that meant that a lot of the queries were accessing the same page. And so because they were accessing the same page, reading data from the same page, that took too much time. The specific action item here is, for example, think about changing your shared buffer settings, think about changing the working set of the data. Another case here, this is from the same GitLab case study mentioned earlier. GitLab ran into subtrends control lock on the W lock wait event, which is basically waiting for that SLU cache that I talked about earlier. In their case, they were in an old Postgres version where they couldn't change the cache size, and they also had too many subtransactions, right? But the wait event was what led them to basically be informed about this. And so the thing to know about wait events is they all have different meanings. Not all of them are a problem, right? Like client read is perfectly fine. But basically, if you keep being bottlenecked on something that's not, a client type wait event, then really prioritize understanding it. So this is something I would say you should have an understanding in your database team what the wait events mean, right? Like what is the function in Postgres basically that's being bottlenecked. All right, in conclusion, I think it's important that you understand which kinds of workloads you have ahead of time. This will let you take preventative actions like tuning settings, reindexing on a schedule, things like that. Wait events will remind you of these characteristics, but it might be too late if the wait event spikes and things are really slow. I do recommend monitoring high-level metrics, right, to let you understand things like where's the I/O in Postgres, which SLU is being used, and such. You can understand things like, are we using lots of subtransactions? Are we using listen notify a lot? But then really, if you are looking into individual actions like a reindex, you do need to drill into per table metrics. And again, this is what we do at pganalyze, right? It's like we do a lot of these per table, per query analysis. So if that sounds interesting to you, you're not a current user of pganalyze, definitely reach out to us and we can tell you more about how that works. All right, I'm right on time. My apologies for running a little bit short there for Q&A, but I do want to take 5 more minutes for Q&A. If you have to leave because you have another thing to get to, we'll send out a recording of this as mentioned over email as well. But I'll take 5 more minutes now for questions, and then if we don't get to all of them, we can follow up async as well. All right, let me see. Give me just a moment to read through the questions here. All right, there was a question earlier that Aaron asked about, is synchronous commit set per session and not per table? So if you recall the synchronous commit setting we talked about earlier, that one is a per transaction setting. So it's really like, it's close to per session, but you can even change it multiple times per session. You can just do set, on your connection, and then that will basically take effect for whatever you're committing next. So something that your application can basically influence could affect multiple tables. Let me see. All right, there was a question of a pgstattuple that Francois had. So the question was, I think, which version of Postgres supports pgstattuple? So pgstattuple, again, is useful for table and index bloat. So you can use pgstattuple in basically any Postgres release. It's in contrib, so you have to make sure you have the contrib package installed. But then you can just create extension pgstattuple, and then that will give you the information. Important to point out is that stattuple has overhead, right? Like it has to read a lot of the data. There's an approximate function which has some trade-offs, but basically read the documentation when using pgstattuple. And then so let me talk about this. So Carlos asked to elaborate why vacuum full is not recommended. If you remember, we had a slide earlier where we talked about, vacuum, like you shouldn't use vacuum full, you should use repack or squeeze. So the reason vacuum full is bad is because it takes an exclusive lock for the time of you doing this operation, right? Like basically when you start vacuum full, like it will force every other activity on a table to stop, right? Like to be locked or blocked. And so that's why you don't use vacuum full on most production databases, is because you have concurrent activity. And that's really what squeeze and repack do for you, is they let you have online like vacuum full operations, basically. If you have a use case where you don't have a workload all the time, like maybe you query your Postgres once a day for a batch job, then vacuum full could actually make a lot of sense to run in the off hours if you're sure that there's no other activity. Let's see. There's another related question on PG repack. So Evgeny asked, is it safe to use PG repack for a table which is logically replicated to a remote? So if I have PG repack, can I just use that whilst I'm logically replicating? So I think I would probably research this just to double check, but I think it should be safe. I mean, basically, what repack will do underneath the hood is it will make a new table and then it swaps out the file nodes, which like it pretends to be the exact same table afterwards, but I would want to double check some of these safety guarantees myself before fully trusting that, to be honest. But yeah, look for probably in the PG repack GitHub repo. It's worth pointing out that the mechanism that repack uses is differently underneath the hood than Squeeze. Squeeze actually does a logical replication to itself, basically. That might be better for your use cases to use PG Squeeze. Let's see. All right, let's see. Afton had a question. We're experiencing 100% CPU utilization on our Nimble storage system that hosts our Postgres database. We're seeing queries hang for many minutes at a time. What diagnostic approaches, potential solutions would you recommend for the storage-related bottleneck? Um, so Afton said CPU utilization, but then also said storage. So I'm not sure which one of the two it is. But I would look for what we talked about in terms of which query-related metrics to look at. I think I would probably look at stat activity first to see which wait events you're bottlenecking, right? So basically, just to that was my share going away. Let me share that again just to make my point. Let me just see. And now my Zoom is gone. There we go. All right, the slide I want to go back to was this one here. So if you have 100% CPU utilization, what you probably have is you're probably experiencing close to something like what GitLab was experiencing here. So all of your queries are probably running into one particular wait event. And so I would recommend getting this type of information, right? Like either this is, I think, an internal dashboard that GitLab did, or pganalyze can also do that for you. There's other tools like Performance Insights can do that. But basically try to understand what are your connections busy with. I think that's the starting point. And then what wait event are they busy with? Based on that, you could then go and investigate the different subsystems. If you have Postgres 16 or newer, I would probably look at pgstat.io as a mechanism to basically, look which part of Postgres is causing I/O. But for anything that's CPU related, I think wait events are a great starting point. And if you have your own Postgres on a virtual machine, that case, I would actually recommend looking at perf profiles. So basically go like more lower level on the system to really dig into what's taking the CPU time. And see, we have a lot of questions, so I'll maybe do two more, three more, and then I think we'll stop just in the interest of time. But we will get to all of your questions asynchronously, so we'll include responses to them in the follow-up. Just scroll down here a little bit. Let's see. Oh, lots of good questions. I apologize that we don't have time to go through all of them, but let's see. Why don't we go back to the early one? Yeah, maybe this is a good question. So CC asked, if a Postgres system encounters many wall-related WLOC wait events, does increasing the wall buffer setting help to reduce these wait events? So I would look for these specific wait events, but certainly it could, like wall buffers could have an impact on this, right? So basically, if you see like maybe it's important, maybe this is useful to share. Each wait event, there's a place in Postgres where the wait event gets triggered, right? So if you really want to dig into it, you can look at the source of Postgres and say, where is this wait event being produced? And so I would try to say, what specific wait event are you seeing? And which part of the wall processing is that in, right? Like, is it basically before data can be written into wall? Like, is there some lock that maybe is being held? Is it when it gets flushed out to disk, right? And so I think I would have to know which exact wall event you're talking about. But I think wall buffers does, like in my experience, does have an impact on some of these wait events. In other cases, you might want to think about, again, synchronous commit comes to mind as something that greatly influences how, write activity influences what happens on the Postgres side. All right, and I'll get to one more question, and then the rest of them will do async. Let me see. Maybe I'll do this one just because it's related. So Eugene asked about how do we properly configure the background writer to avoid writes in backend processes. So this comes back to, related to wall, but it's basically related to, it's related to the dirty buffers, right? So we have Postgres accumulating the shared buffers, the dirty buffers and the shared buffers. And the question is, how do we configure the BG writer to avoid the writes in the backend processes? So if you know that you have writes in the backend processes, as mentioned, pgstat.io can do that for you, then you can adjust the background writer to run more often. So basically just tell the background writer to do more work more often, so that it does these writes ahead of time, right? So the basic motivation is basically, if you can get the background writer to do its work before the backend, the client backend needs the space, then that's what you're trying to achieve. Alternatively, what you could also consider is increasing shared buffers. Sometimes it can make sense to basically just give your workload more space. We didn't talk about shared buffers much today, but it's worth noting that the default recommendation of 25% of shared buffers for RAM is a bad one, right? Like you shouldn't use that setting. It's really not that efficient. And so, for example, if you see yourself, needing a lots of space in your shared buffers, it might make sense to do something like 50% of shared buffers, just to basically give Postgres more space to work with, and that includes, the more space for dirty buffers to be present, basically. Um, all right, I'll stop here since we have actually 40 more questions. So, if I kept going, we would be sitting here for half an hour, and I'd be exhausted. But we will get to all your questions, as mentioned, asynchronously. And so we will send out an email tomorrow with basically a Q&A section where we get to them in text bases. And then if you have any more questions about pganalyze or, about the content talked about today, feel free to, reach us on our website. There's a contact us form. And then also my email was in the very first slide, which you'll get that tomorrow as well with the summary email. So thank you again for joining. I really appreciate everybody taking time out of the day today.